Ayan, okay. So the purpose of this live discussion is so that you have a focused time to study the material. Unlike the usual online, what they call this, discussions, if it's synchronous, sorry, asynchronous, and you just look at the video lectures, you tend to procrastinate, or we pretend to procrastinate, and then we get lost with our time. So let's try this so that just like the old days, we are focused at the given time only. All right. So I think I mentioned earlier that all these classes will be in like 80% English or 90% English with 10% Tagalog because we're trying to provide these classes open source as well. Or at least the lectures will be uploaded on YouTube, and anyone who has the link or will actually be listing it. So anyone who needs these materials, uh, Microb is providing it publicly for everyone. All right. So let's begin. Welcome to CoE 113, Advanced Computer Organization, and this is our first lecture about performance and metrics. Okay. So if you have questions along the way or something is unclear with the explanation, you can just stop me, just open your mic and just say, or just ask questions or drop the questions in the chat box. Okay. Okay. Let's begin. So this the first and foremost. Actually, yeah, it just helps us give us context on what we're trying to work on by the end of this course. Because ultimately, what we want to do is to make a RISC 5 32-bit processor. And the first things that we usually do at first is to provide context. Why in the world are we trying to make a processor? Now, the motivation really is that we can only understand how the benefits of this type of architecture, that type of architecture, based on performance metrics, right? So hold on, let me bring out the pointer. Right. So really, what we want to do at first is to understand, okay, how do we measure performance between processors? Because that's the only way to determine, hey, is processor A or B, is processor A better than processor B or processor C better than processor B? We don't know. And the only way for us to know is that we have to understand the metrics, especially the thing that we call performance metrics, right? And it's good because this is the only way we could actually, hey, make proper comparisons. It's not subjective, basically. It's more objective in a way, right? So there are many factors affecting this metrics, right? First and foremost, of course, is design of hardware. Sometimes maybe the processing unit, the one that works on the operations like addition, subtraction, multiplication, maybe processor B is not so good, processor A is may much better because of parallelism, things like that. The types of machine language instructions, this actually is very important. For example, between ARM, RISC, and MIPS, sometimes ARM looks a bit more tricky to do, but apparently it provides a lot more flexibility compared to MIPS and RISC. Algorithm-wise, this is more on the software side. Compiler efficiency, also a bit more on the software side, actually software hardware. And of course, implementation technology, whether in 45 nanometer technology, 8 nanometer, things like that. Okay, but for our purposes in this class, we'll be mostly looking into these two: design of hardware and the machine language instructions. Compiler efficiency and algorithm is much more for CS people. Implementation technology, that's more. Actually, this should also be part, but let's say it's a bit more on the graduate class because there's a lot of things that you have to consider here and too many setups. Okay. So at least for our class, we'll be focusing on this. So list of basic metrics. We have clock period. I think that's pretty much taught to you before. Clock cycles, execution time. This is more of response time. Throughput, a little bit also the same, but throughput is a bit more, okay, how much data can you actually process? Elapsed time is actually a little bit more like execution time too. CPU time is a subset of elapsed time, and then you have the overall system performance. But we'll be focusing on this, 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 and this. Okay, most of our classmates will be classmates. Most of our uh, discussions will be about those basic metrics. All right. First and foremost, clock rate or the period of the clock. You see, digital processors are most of them are synchronous circuits. Actually, let's say all of them are asynchronous circuits. Asynchronous circuits or asynchronous systems are very rare. They're very hard to develop. So what happened historically is that hey, synchronous circuits works and it works pretty well for several processors. Let's stick with that. And the thing is, it's governed by a constant clock rate. It's the beating heart of the processor. Without the clock, no, none of the data will be transferred at every clock cycle. Now we have the definition of a clock period. It's the length of one clock cycle. How long in terms of time is measured in seconds. So pretty much from edge to edge, that's just one clock period. If you take the reciprocal of the clock period, you get the clock rate. So it's the, well, it's also another interpretation actually is the number of clock cycles in a given second. Okay, and it's measured in hertz. So yeah, it's a very simple concept. The more important concepts right now would be the definition of execution time and processor time. Execution time, it's the total time, okay, required to execute a program. Say for example, if you guys are actually most of your the generation that you're in, you're very game MMO or multiplayer oriented people. So let's say you have this program wherein you have the game Valorant where you have to click to shoot, and they have this program that is click to shoot, and you have to get the execution time. So execution time is from starting from the input output of a mouse button, and then later on it gets transferred to the CPU so that the CPU assesses, hey, okay, what did this person do? Did he click to shoot? Did he right click or did he left mouse button? You don't know. And then once it's understood that it's a left click to shoot, maybe it updates the GPU time to update the whatever you're seeing in your display, all the vectors of the bullet, all the positions of the players, all those things, anything graphical. Okay, and then it transfers again to the CPU and says, "Hey CPU, this is the data that you need. You're gonna have to display it in your LCD screen." So the entire thing here, from the beginning up to the end, is the execution time. Okay, so that's the total execution time of a program. Inside the execution time, a subset of it is the processor time. So this is something that we'll be looking at throughout this lecture. It's mostly processor time. Okay, so it's time needed to execute the program or a piece of the program inside a processor. That is, let's say your processor is an Intel processor or an i7 or an AMD. Or let's say we're ambitious that we are looking into, you don't know, a RISC-V processor that's doing Valorant things. Okay. Basically, it's just the things or the time, the CPU time, literally the central processing unit time that's being executed in the program. Okay. So in this case, the CPU time here, from here to here, is just the total CPU time for this part and this part. And then if you add them both, that's the total CPU time that you get. Okay. So it does not include the time given for the input output, the GPUs, the operating system, and all other peripherals. It's just literally the time when the processor is active. And the reason why we're looking into this is because most of the time, the central processing unit is the one that's working the most. All right. So even if you try to open your task manager, you would see that your CPU is the one that's running like, how would you call it, 100% of the time, something like that. GPU only when you're accessing or playing games, but in all other applications, it's always the CPU time that's always running. All right. So the big difference between execution time and CPU time is that execution time is the entire program, but CPU time is the subset or a part only of that execution time. That means it's only looking into, okay, how much time is my CPU actually running? Okay, so simple. Now we're going to focus more on the CPU time and how do we actually calculate CPU time. So the best way to understand this is really try to give it some thought on how to actually calculate CPU time because it only consists of two things or three things rather. The number of instructions, I, the cycles per instruction determined by the CPU hardware and the clock rate. Okay. So we'll be going a little bit of ahead of the discussion here, but when we talk about cycles per instruction, you see, because all programs are written in instructions. That's the bare bones thing. You write a C code, you write a Python code, eventually it will become a list of instructions. Okay, and those instructions are processed by the CPU. But the CPU, when you plug it into your CPU, the best CPU hardware out there processes instructions with a cycle per instruction of equal to 1. That means for every single clock cycle, okay, from end to end, it processes one instruction at a time. However, not all CPUs do this. The best do. No power CPUs, embedded processors, maybe not so much. It really depends on the design. No, actually, I think they do too, but more complicated CPUs like the Intel or AMD, uh, they do it more than one clock cycle. They process one instruction in more than one clock cycle, probably 2 to 5. But because of pipeline, it approaches to one instruction per cycle. Okay, so there are many other underlying layers for that. But the important part is that if you multiply the number of instructions with the cycles per instruction, so that's like instruction times the number of cycles, how many clock periods per instruction you get, right? You get the total number of cycles, right? But we know that the number of cycles is related to two things. Okay, the clock rate determined by the CPU hardware, that's the F over here, or we just know it from previously the period clock T, right? So if you multiply the cycles by the period, you get the what? The total number of execution time, or rather the CPU time. Okay, the total CPU time. That's why we put it at CPU T. You can use the frequency instead, the clock rate, but I prefer to use the period because it's more intuitive, right? So you could, well, these two are equivalent anyway, but to make it more, how would you call it, common sensical, to have it more common sense, you use the period. So the total number of cycles times the period gives you the total number of CPU time, right? It's very simple. Now, if you take the reciprocal of the CPU time, you get the CPU performance, right? So in a way, you could say if this is in seconds, then you get the CPU performance. It's like in hertz because 1/2 is always in hertz. That's the sort of the translation of it. You could do it this way, but would like to stick with the CPU time because it's seconds and it's much more intuitive. All right. So the thing is, for the same task, different instructions can actually be used, resulting in different number of instructions and the number of cycles per instruction. So it depends. Say, for example, between an ARM processor and the RISC-V processor, because they have different compilers, you would say that maybe for the same sorting program, let's say, maybe the ARM would probably do it in 100 instructions, but with a CPI of maybe 1.5. And then the RISC processor maybe would be able to do it in 125 instructions because ARM has more flexibility compared to RISC-V. But then the RISC-V actually does it in probably, what do you call it, less than number of CPI. Let's say this is CPI. All right. 1.5 for the ARM, but for the RISC, it's, let's say, 1.2 or maybe 1.1. We don't know. Okay. So between the two, just to do the sorting program, you can actually calculate, hey, which one of those processes the least number of total number of cycles, but you also have to relate it to the total number of operating seconds, or what's your cycle time. Okay, it's very easy, right? It's the only thing you have to know. Any questions before I proceed? No, just to so you know, this will be our working equation. CPU time is the total number of cycles, which is the number of instructions times the cycles per instructions times the cycle time or the clock period. Okay, it's very easy. It's only just three the values. Okay, so let's oh yeah, before we do go into some exercises, another performance metric that we'd like to look into is what we call speed up. It's basically answering the question, okay, how much faster is this processor compared to the other? Okay, so how fast is processor A compared to processor B? If the speed up ratio, eta, this is eta, okay, eta, is positive or greater than 1, then processor A would be faster than processor B. Otherwise, processor A is slower than processor B. Now, it is very common for students to mix this up, but my strategy really is to, because sometimes you do it in terms of process, CPU processor processing speed, okay, the rate rather than the execution time or the CPU time. So you could do it this way, but then since the processor and the CPU time, the performance metric compared to the CPU time is just the reciprocal of each other. I personally like to do it in terms of execution time. Or sorry, CPU time. Always mix that up. CPU time rather. Okay. And it also makes sense because if let's say processor B takes around 20 seconds and processor A is around 10 seconds, it's very obvious that processor B will always be slower because it executes in 20 seconds. So if you try to analyze the statements clearly or the data clearly, if it's 20 seconds, it processes a specific program or yeah, a program in 20 seconds compared to processor A who's executing it in 10 seconds, then clearly processor B is slower than processor A. And then if we're going to get the speed up, I usually like to set my speed up, my eta ratio, to be the slower one over the faster one. And automatically, if I take the ratio of this, I am sure that processor A will always be 2 times faster than processor B, or processor B is 2 times slower than processor A. Okay, so you don't have to think too much about the equations, but rather let's try to translate it into English because it's easier to understand. Okay, so two things. We have the CPU time and the speed up. That's the only thing we need to do, right? Okay, so easy problem one. Suppose we have two implementations of the same instruction set. Architecture. Machine A has a clock cycle time of 1 nanosecond and cycles per instruction of 2 for some program. Machine B has 2 nanoseconds and a cycle per instruction of 1.2 for the same program. Okay, so which machine is faster for this same program and by how much? Let's assume that the compiler actually produces the same set of instructions. Right. So it's very easy to do. Of course, as we were taught in previous years, write down the given. So assume that the program has 100 instructions, but the two machines differ in terms of cycle per instruction and uh, clock period. Okay, so machine A is 1 nanosecond, that's equivalent to 1 gigahertz, but with the cycle per instruction of 2, machine B processes it slower, okay, but with a cycle per instruction that's much less. So which among those two is actually better, right? So you know this automatically. Also, you know the total number of instructions. Automatically, we just have to compute the CPU time, right? So if you compute the CPU time, it's 100 instructions times 2 cycles per instruction divided by the gigahertz, or you could say equivalent to 100 times 2 times what? 1 nanosecond? That's equivalent to 200 nanoseconds. Machine B, on the other hand, you could also do it that way. 100 times 1.2 times, what's that? 2 nanoseconds? That's equivalent to 240 nanoseconds. And clearly, from the results itself, machine A will always be faster, right? And then by how much, right? If we're gonna do by how much, my strategy all the time is, okay, grab the larger metric divided by the lower metric, okay? That's the next slide. Grab the larger metric, divide by the lower metric, and then you immediately get 1.2 times speed up. But that 1.2 times, because we know that machine A is faster than machine B, automatically we would say, okay, machine A, MA is 1.2 times faster than machine B, right? It's very easy, right? That's the only thing you have to understand. Okay. If you do your homework in your homework one, you have problems like this. So it's just a matter of simple multiplication and ratio. Okay? Any questions here? No questions? Okay, moving on. Easy problem two. The hardware accelerators are okay. So this one is a bit more. We need to do a little bit of analysis. Okay. So hardware accelerators, that's very popular nowadays, especially for machine learning applications, are additional hardware in computer to help speed up certain tasks. Take note, not all the tasks, but only specific tasks. Okay. Suppose we are considering using an accelerator for a specific task. Okay, for a specific task only. That speeds up that task by 10 times faster than the original machine. Let's say you have machine A, okay, and then a part of that machine is, let's say it's the machine learning accelerator. All right. If you don't have that machine learning accelerator and then you're just using the original CPU of the machine A, okay, or let's say the multiply and accumulate version of machine A, let's say A original. Oops, let's try to erase that. So erase, erase. Yeah, A original is just using the CPU, and then the A new is actually using the CPU itself, but with the machine learning accelerator over there. All right. So if I only use the original A just to work on the machine learning task alone, as opposed to getting a new one with a machine learning task, for that specific machine learning task, we can actually operate it 10 times faster. So my eta is around 10. Okay, so that's what it's trying to say. However, the only catch here is that I'm not using that machine learning task all the time. It's only working 40% of the time. So what is the overall speed up brought about by that accelerator, right? So it's a bit of analysis, but it's very easier to do that to understand by doing some visualizations, right? So if I had my original A, right, this is my original A or rig, and then 40% of that entire program is actually due to the machine learning part, and then 60% here, so this is the 40%, and then the 60% over here is the, let's say, untouched part because it's not machine learning, right? And then if I'm going to use that machine learning accelerator, okay, which proposes that it will speed up by 10 times, 10 times faster, what happens here is that for that 40%, let's say it runs 40 seconds rather than 40%, and then all the rest is 60 seconds, right? Um, okay, how much faster will it be if suddenly I brought this down to 4 seconds instead, right? 4 seconds, why? Because it's 10 times faster. So if I have something that runs 40 seconds long, but I reduce it 10 times, then I only have to run 4 seconds. Diba? And then idadagdag nyo, and then you're just gonna add this other 60 seconds here. Right? 60 seconds. Right? So this is the A new. So in total, this is like 64 seconds in total, then A new. But the old one is around 100 seconds. So how much speed up is that? Right? So it's like 100 seconds divided by 64 seconds, whatever that is. Okay? So visually, that's how you're going to approach it. But if we're going to do it the math way, right, we know that we were told 10. Okay, so that 60%, if you're trying to do it with variables only without assuming the number of time. So the CPU new is actually you grab the CPU old, 60% of the CPU old, maybe that CPU time old is around 100 seconds. So this entire part here is around 60 seconds only. And then, of course, the CPU accelerated, it's 40% of the time, right? But that CPU2 accelerated is like a ratio of the old, and then you have to integrate that times 10 speed up there. So that's the 4 seconds later on because you speed it up. So you get around that, you know, essentially it's 0.64 times CPU-T old is that 64 seconds old, right? So if the CPU is old, you could do it this way, ratio and proportion. But if it's like 100 seconds or 64 seconds, if you do the ratio, you get around 1.5625 speed. Okay. So you could do it either Actually, I prefer to do it this way where you try to visualize it, or you could do it this way that you do algebra instead. Okay, so either process works, right? This one, doing it visually is much easier to understand. Okay, any questions? None? Okay, so there's a new concept. We call it the Amdahl's law equation. It's actually a derivative of what this is, right? But what it tells us is that, okay, what's the total time of my improved version? Or rather, the total time of my improved version will be the total time, the fraction of the time that needs to be improved. How much time are you going to improve it? Plus the time that is unaffected. In our scenario earlier, we had that 40 seconds here and the 60 seconds, right? For the old version, sorry. So how much time is improved will be, okay, this component here refers to the time that needs to be improved. Okay, so it's this 40 seconds, right? And then you divide it by how much time are you gonna improve it, right? So earlier we said that the eta is 10. We want to improve this 40 seconds by 10 times. So you reduce it by 4 divided by 10, 40 divided by 10, right? You get the 4 seconds time remaining. That's how much time is improved, right? And then you just add the part that's unaffected, 60 seconds, right? So that's actually Amdahl's law equation. And there's something very interesting about Amdahl's law, which we'll try to interpret in a while. But this is like the equation or algebra version of this visualization. All right. So let's try another example. Suppose you have a program that runs in 100 seconds on a computer, okay, with only multiply operations responsible for 80 seconds of this time. Okay. How much do I have to improve the speed up of my multiplication if I want my program to run in 60 seconds? So visually, what we could do is, okay, draw it again. This is my entire 100 seconds, but 80 seconds of the time is meant for uh, what do you call this? For multiplication. But the other 20 seconds is meant for things that are not affected by multiplication. The question is, I want to achieve 60 seconds only. I want my final form. I didn't draw it properly. I want my final form to be 60 seconds only, right? But how much of my multiplication needs to be reduced, right? I'm exaggerating that. So let's say, no, yeah, that's right. Let's say this is 20 seconds. This is the untouched time. And this is, okay, how much time do I need, right? Well, visually, if the untouched is 20 seconds of time, then I need the remaining 40 seconds, right? I need my multiplication to be 40 seconds shorter. So if it runs originally 80 seconds, it's the old, and then the new is around 40 seconds, then how much speed up do I need? I need a speed up of what? From 80 to 40, you only need a speed up of 2. Correct? Mathematically, so this is visually. Okay? Mathematically, you could write it this way. This is my target speed up, 60 seconds. The amount of time that needs to improve is 80. The time that is untouched is 20. And then you have the k here. Okay, how much speed up should the multiplication be? So solving for k gives you 2. Right? That's simple. Okay. Now, here's an interesting scenario. What if I want my speed up? Okay, what is the speed up k if I want my program to run exactly 20 seconds? Okay. And if you do the math over here, if you move 20 over there, that becomes 0. 0 is equal to 80 over k. That does not make sense anymore. In fact, it is impossible to make it that way. Okay. It is impossible to make it that way because if you try to analyze what Amdahl's law is saying is that you actually have an asymptotic improvement. Okay? Say if I want to get my new speed up, my T new, right? And let's say let's use this the same thing, 80 over k plus 20, right? There is a maximum T new that you can achieve, or rather, the minimum TM that you can achieve, and you cannot get any lower. And what is that? It's actually just 20. Actually, a little bit higher than 20. Why? Because if you analyze the equation very carefully, this form here is of the form of 1 over x, right? And if you plot that in a scale that's asymptotic to zero. You can make x, or you can make the speed up very, very large. You can make it up to 1,000,000, right? But the final result, this term here will approach zero, right? But your t nu, okay, will only be asymptotic to 20 seconds. You cannot get 15 seconds or less. Because in order to get 15 seconds or less, or anything below 20 seconds, that the untouched part needs to be reduced. But no, you're only touching only a specific part of it, right? So this equation over here, if you do the math, if you analyze it very carefully, you have an offset of 20 seconds. Right? That's 20 seconds over there. And then this speed up ratio over here is what? Asymptotic. You can never get below that anymore. Okay. So that's very interesting about Amdahl's law. It tells you, okay, how much speed up, or what's the limitations of my speed up. Okay. Okay. Any questions? None? Okay. Uh, from here onwards, it will be all about exercises. Right? It's just a review. What we're gonna do right now, everything from here onwards, is just to review all those concepts. So again, before we start solving this, just to review the concepts that we only need is the CPU time, which is just the total number of instructions, cycles rather. So instructions times the cycles per instruction times the time, right? You have the eta, which is the longer one, the CPU time of the longer one over the the CPU time of the shorter one, right? And then you have Amdahl's law, the T nu is equal to the T that must be improved over the amount of improvement plus the T that is unaffected. Okay. So yeah, see, these are just the working equations that you need. Okay. All right. To make it a bit more lively, or just to see if you guys are still there, let's try to solve it. But I'm gonna ask you questions. All right. So for example, uh, for this easy problem, right? We wish to compare the performance of machines M1 and M2, and the following execution times were observed. CPU time is 10 seconds. For a program 1, CPU time is 10 seconds. For machine 1 is 10 seconds, and then CPU time for machine 2 is 5 seconds. But for a second program, CPU time for machine 1 is much faster than CPU time of machine 2. Okay. So based on this information, which must okay, try to understand this question very carefully. Which machine is faster for each program and by how much? So essentially what we're trying to get is the eta. Okay. So for program 1, any of you would like to answer, who is faster? Machine 1 or machine 2, and by how much? Anyone? They want me to roll call? Let's roll call. Para, just to get a bit of interaction. In my list, Jan, you are number one in my list. For program one only, is machine one or machine two faster, and by how much? Are you still there? Or am I still here? Machine 2 by eta of equal to 2. Okay, very good. It's very easy, right? So machine 2 is definitely faster because you just have to look at the execution time, so CPU time. It's 5 seconds. And if you divide the longer time by the shorter time, you get it by 2. Okay? Okay, for program 2, Mads, how much? Who's faster? Machine 1 or machine 2, and by how much? You can type it or you can speak up. Okay, pag-speak up para recorded din. Program 2 lang, ah.
Machine 1 is faster by 1.33 times.
Machine 1 is faster by 1.33 times. Teka, ako din. I need my calculator. What is 4 divided by 3? Is that 1.33 times? But yes, you are correct. Machine 1 is faster because it's 3 seconds. Hold on. Let me see. 4 divided by 3. Yes, you're very correct. Okay, so 4 divided by 3. is 1.333 times. Okay? It's very simple, yeah. Okay, next. Oh yeah, so there's the answer. I forgot I put it here. Okay, same thing, but assuming program 1 has 200 uh, mega instructions, and both M1 and M2 have 200 megahertz and 300 megahertz respectively. Find the cycle per instruction for M1 and M2. All right. So take note. We're only looking at program 1. We're gonna ignore program 2 for now. So we're gonna just program 1. Okay. So I'll solve this for now so that we can go uh, a bit faster. Uh, so program 1 has 200 mega instructions. Okay, times CPI, because we don't know the cycles per instruction, okay, times or divided by the rate. Okay, for M1, this is 200 megahertz. Okay, and then for M2, that's just what 200 instructions as well times CPI or divided by 300 megahertz. Whoops, I forgot to put the CPU time. The CPU time for M2 is 5 seconds. CPU time for M1 is 10 seconds. Okay. And then what we're gonna do? We're just gonna solve for CPI. Okay. And if you do it correctly, you should get. See, machine one has a CPI of 10, and machine two has a CPI of 7.5. Okay. Now the bigger question is, okay, if I have a CPI of this much, right, does it automatically mean that machine two is definitely better than machine one? Okay. And the quick answer is for if we have to make assumptions, right? If the assumption is that you're just only given this amount of instructions, then machine 2 will definitely be better than machine 1. Why? Because remember, the execution time is CPI times the period times the instructions, right? And then that's the CPU time rather, right? And if of course if CPU time is very much slower, our target is to make CPU time lower. Then if CPI is very much lower, then you get the faster processor. Okay, but that's assuming if all the instructions are the same, right? Because sometimes some instructions, let's say load word instructions, some processors have very long. Sometimes the load word instruction is just, let's say, both A and processor A and B are one, but the multiply instruction sometimes differ. For A, it's around, let's say, 2, and then for B, it's 3. Okay. And then you have the divide instruction. For A, it's around 3, and then B, it's around 2. Right. So there's a instruction mix going on. So there are problems like that. And I believe that's one of your homework. That's one of the questions in your home. Okay. So just to make sure you have to, the bottom line is that you have to make assumptions. Okay? You have to assume. Okay. Let's see, we wish to compare the same thing, but if M1 costs $10,000 while M2 costs $15,000 and you only run program 1, which machine would you use? Let's assume that we're only basing it on this execution time metrics, right? So again, machine 1 costs $10,000 while machine 2 costs $15,000. So let's try Paulo. With that, just give me an idea what you think. Which one would you choose? Okay. And why? Well, I think that follows why. Right? Would you choose machine one or machine two? And knowing that the execution time is this much. Are you still there? Am I made that there? Or maybe Tim, if you'd like to try?
Ah, yung yung 2, sir, machine 2.
Machine two, okay. Give me a good reason why. Let's think about it.
Because machine 2 is 2 times faster than machine 1 in terms of the time. Pero
Is it?
it's 1.5. Tama ba, sir? Para 1.5 much more expensive than machine 1 in terms of
Ah,
price.
okay. So you're saying, okay, that's a good answer. Okay, that's very valid. So team was saying, okay, machine two is better because the price is just 1.5 times higher at the cost of you're getting two times speed up, right? That's what you're trying to say. So this is the cost. The cost is just 1.5 times higher, but I'm getting a speed up of two times. That is a valid reason. And yes, I would agree that's a very good reason to do so too. And I would say, okay, if you put it in that context, yes, I would say that's also correct. All right. There's another way to treat it is that sometimes people don't care about the cost. If you're a very rich person, you say, okay, I'm just gonna get two, the M2 because I still get two times speed up. I don't care about the cost. But sometimes people do it this way. That what they do is that they multiply the cost, okay, 10,000 by by the CPU time. So you get something like 10K dollars times 10 seconds. That's like let's say 100K uh, $1,000 seconds. How do I write that? Dollar K times seconds. And if you multiply it here too, that you have what they call this, the 15,000 times the 5 seconds, you get this, how do you do that? 15 times 5 is around 1, 2, 3, 4, 60, 75,000 times dollar seconds, right? Sometimes people make these weird metrics. Okay? They like to combine things, divide things, multiply, but these are valid reasons too. But it's consistent with what you said that, okay, maybe machine 2 is a much better option because even here, what you want to do is that you want to have the least number of, the reason why you can multiply them together is because one, you want to have the least number of dollars, and at the same time, you want to have the least number of seconds too. And in both cases, machine 2 is the winner. Okay? So that's a valid what do you call this? A process of thinking of trying to deliver, picking out, right? Yeah. Okay. So that's the one. Okay. Harder problem one. We have 15 minutes left. I'll speed through this. Okay. Given two different machines, M1 and M2, using the same instruction set architecture, M1 has a clock rate of 2.5 gigahertz and M2 has a clock rate of 3 gigahertz. The instructions can be divided into three classes, A, B, and C. This is the instruction mix I was talking about earlier. Now, the CPI for each class is shown in the left table. Okay, so for example, instruction, let's say machine learning instructions, memory instructions, and I don't know, let's say what's in between the two? Sorting instructions, right? Let's just give it a name. Okay, so for different machines, you have a set different number of cycles per instruction per instructions. Okay, so it differs. Now, the thing is that instruction mix for a certain program generated by two compilers, C1 and C2, is shown in the right table. Okay, because let's say you have an AI program, right? And then the number of machine learning instructions they have to do is for compiler one, okay, is around 55% of that machine learning instructions. Okay, and then this is sort. And then for 40% for the memory, 5% for the sorting, and things like that. Okay. So don't please don't be confused that compiler one does not mean it belongs to machine one. Okay, these are independent of each other because compilers are software things, machines are hardware things. So if you have a compiler, which is software things, these are independent. Okay, that means I can run this set of instructions or compiler that compiler one spits out for machine one or machine two. Okay, that's the idea of it. Okay. But let's say assume that the compilers generate the same number of instructions. So they have equal I1 and I2. But the instruction mixes are different, meaning you have a different number of, okay, how much cycles per instruction do you actually need for compiler 1 and compiler 2? Okay, so we'll screenshot that for now. Actually, since this is recorded, we can go back to it later. But the question is, okay, using compiler 1, which machine is faster and by how much? And using compiler 2, which machine is faster and by how much? Okay, and take note of the question. The question is, okay, I'm going to plug compiler 1 to machine 1 and machine 2. At the same time, compiler 2 for machine 1 and machine 2 later on. Okay. But let's do compiler 1 first. So for compiler 1, the simple strategy is to get the total number of cycles and then you multiply by the execution time or divide by the clock rate, right? So it's simple. And it's ratio and proportion. And we can always assume, again, make assumptions that both instructions for machine 1 and machine 2 are equal. There are just 100 of them, right? And for machine 1, it's just ratio and proportion, right? So for machine 1, okay, since you're using compiler 1, so 55% is used for compiler A, for instructions A, 40% is for instructions B, and 5% is for instruction C. So if you're using machine 1, what you do is that, okay, you multiply 55% of that 100 instructions. Okay, that's the total number of instructions that you see that is using instruction A, and then you multiply it by the CPI 2, right? Same goes for 40 instructions is using instruction B, and then you multiply it by 3 because that's the CPI of machine 1. And then 1 for C, of course. Get the total number of cycles, divide by the clock rate, or multiply its execution, that you get 94 nanoseconds. Same goes for machine 2. You have total number of instructions. Oh, sorry. Yeah, the total number of instructions for instruction A. Take note, you're not changing the number of instructions because you're pertaining to compiler 1 only. Okay? What you change is the cycles per instruction, right? And then you eventually get the total number of time, which is 150 nanoseconds. And who is faster? Machine 1 or machine 2? Machine 1, because definitely it's 94 nanoseconds, right? And by how much? It's around 1.22 times speed up, right? Pretty easy. For the case of C2, you actually use the same number of cycles per instruction, right? That's the same as the previous one, but you change the number of instructions that's being affected, right? And bottom line, between 88 nanoseconds and 86.67 nanoseconds, machine 2 is definitely much faster. Okay, by only a few much. So between the two, would you rather choose machine 1 or machine 2? Right. And in a nutshell, I think machine 1, based on the given data that they have, would most likely have a better speed up because it's around 1.22 times compared to machine 2, even for a different compiler, okay? Or even for a different set of instruction links because ultimately it's still faster, right? Even though machine 2 is faster by only just a little bit. All right. Okay. Uh, this is the last problem. Actually, is it? I'll screenshot a bit. Oh, yeah, 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 yeah. Last problem. No, not the last. Second to the last problem. Time check. Yeah, we can do it in 9 minutes. Okay, implementations of floating point square root vary significantly in performance. Suppose floating point square root (FPSQR) is responsible for 20% of the time of execution time or CPU time of a critical benchmark on a machine. One proposal is to add FPSQR hardware that will speed up this operation by a factor of 10. The other alternative is just to try to make all FP instructions run faster. Okay? Or FP instructions are responsible for, sorry, the other alternative is to try to make all FP instructions faster, but FP instructions are responsible for a total of 50% of the execution time. Okay. The design team believes that they can make all FP instructions run 2 times faster with the same effort as required for the fast square root. So which of the two design alternatives would you choose? Now this is easier again when visualized. So it's the same thing that we did earlier. Okay. So for case one, let's assume again that we have 100 seconds total execution time, right? And we want to make in both cases two time we want to determine, okay, which among the two cases will actually be better for our purposes. And what are those two cases? The first one is that this is case one. One proposal is to add the FPSQR hardware, the hardware acceleration, which speeds up the operation for that floating point, okay, However, it's only working for 20% of the time. Right. So for the old case, right, it's 20 seconds of the total execution time. And if I add that FPSQR acceleration, it reduces that 20 seconds to 2 seconds. Kasi 10 times, because it's 10 times faster, right? That's over there. And of course, there's the untouched part, that 80 seconds. You get a total of 82 seconds overall. Case 2, on the other hand, is okay, let's make all FP instructions that are actually 50% of the time. All right. But you can only make it 2 times faster. Right. So 50% of the time, okay, there's an untouched 50 seconds, but you make all of these 2 times faster as compared to the 10 times faster of the other version. Right. So if you make it 2 times faster, you get 25 seconds. And if you add both cases, the sped up version and the untouched part, you get a total of 75 seconds, or rather 75 seconds. It's very easy to visualize, right? So overall, case 2 is faster by an amount, by just a little bit, around 1.093 times speed up. All right. Yes, again, very easy to do. If you like to do Amdahl's law, it's really up to you. All right. Okay, so there's one more metric actually, which we call the power and energy metrics. All digital circuits can be estimated like charging or discharging a capacitor with a transistor. Right? I won't be going into detail anymore, but the way we measure power and energy. See, power is important because it's indicative of how much heat are we dissipating, and energy is indicative of how much, from the name itself, energy are we actually absorbing or consuming to process information, right? And every time you process data, let's say in an adder or an ALU, right, you spend energy to process that data. You don't care how fast you do it, because usually fast circuits is proportional to power. Okay, so the speed, F, as you can see over here, right? But then energy is not dependent on speed, or yeah, it's not dependent on speed. It's rather dependent on how much computing you do. But we'll get to that next time. For now, one of the key things that you have to understand is that, okay, most digital circuits, like an inverter, this is a simple inverter, okay, logic inverter over here. Uh, we actually estimate the power depending on, okay, how much do you charge the capacitor, or how much do you discharge it? Actually, no, not discharge, but rather the charging of the capacitor, right? So you actually charge it by some fraction of a ratio. Like if you have a inverter here, and that's processing in some big processor that you have over here, okay, how much percentage of that inverter is actually toggling, right? And for every toggle, particularly the rising edge of the toggle, because the only time you consume energy is when you are charging the capacitor. When you're discharging it, you're not consuming energy. Okay? Only when you're charging it. When you discharge it, it's like throwing away the energy stored in the capacitor. So that's fine. But we are interested in getting the, okay, how much is my switching ratio? Okay, that's why we indicate that 0 to 1 switch. How much of the time am I actually charging the total number of inverters or ALUs or any digital circuit in a form of a capacitor? Okay, so how much time am I actually switching the capacitor? Okay, so it's a fraction. That's why the alpha fraction here, factor here, is called the switching factor. And then you multiply it to the total capacitance of the processor, okay? Because we're treating all the charging of capacitors. We're not, see, a processor may have a gazillion number of capacitors. Okay? You don't know how many of that there are, but how much ratio from 0 to 1 are you actually charging it? And then you multiply it by the voltage squared, the operating voltage, because that's how much charge you're actually dumping into the capacitor. And then you're multiplying it by the, okay, what's the rate? How fast am I actually charging that? Okay. And then the I leakage here and V is due to the transistors, because, from your semiconductor physics, there is leakage going on through our transistors. Okay. So power is defined this way. This is like a first order estimate of power. It's dependent on how much is switching from 0 to 1, multiply the total number Actually, this alpha factor is the switching. How much is switching from 0 to 1 and how much of the total capacitor of my digital circuit. It's like a ratio. Okay. Usually in cases in low power processors, like maybe 10% of it is switching. Machine learning processors are like 80% of the time something is switching. Okay, so something like that. But you need sophisticated tools to measure that. But it's a good estimate. And then that V squared there is the total number of charge being stored into the capacitor when you charge it. F here is actually time, right? In a way, this chunk here is actually the energy. Okay, so that's energy. But power is defined as energy divided by time, right? And if you do the math correctly, that's energy times the frequency because time is the time or the period for a clock cycle is 1 over f, right? So that's the estimate for power, all right? Energy, as I mentioned earlier, the next one here is just uh, you can translate it to from power. You can translate it to energy. Okay, so it's literally power times the period, or that's equivalent to power times the sorry, not period, but f over times 1 over t rather, or power times the frequency, right? Because energy is independent of time. Okay, that's how you get energy. Okay, so what do you do there? You power times the period. If you do the math correctly, it cancels the frequency, right? Because t is 1 over f over there. If you take out the time component, you actually get the energy component, right? So this factor over here is independent of time, right? That's why I was saying earlier that the amount of energy that you use to charge or discharge a capacitor is independent of time. We don't care. But what we care rather is how much times are we actually switching the logic gate. Okay. Now, of course, leakage here is more of that's something that's the leaky currents that are going through. It's also a component that you have to consider. Okay. And if you observe here, V times I is power, and then if you multiply by time, okay, you get the energy. Okay. So mali pala to. You have to multiply power by time rather, and then you have to divide it by frequency over here. Okay, that's the correct version. Okay, so very quickly, suppose an embedded processor has a switching ratio of 0.01 as with a total capacitance of 250 picofarads. Let's say you had some tool that was able to measure it. The operating frequency is at 1 megahertz and the operating voltage is at 1 volt. Assume that leakage is negligible due to small size only. Okay. Usually leakage starts to become a problem when we have big circuits. But if it's small, you don't care. What is the estimated power and energy? Simple. Plug and play the equation. Alpha, C, total capacitance. The operating voltage is 1 volt. Okay, this is just 1 squared. Times the frequency, 1 megahertz. You get around 2.5 microwatts. So that's relatively low. That's somewhere around, low power Bluetooth. Okay, low power Bluetooth. Okay. Actually, they also call it the low BE. I think the low power Bluetooth energy. Okay, if you calculate the what do you call this? The energy. You just multiply uh, or you just divide the frequency rather, or just multiply everything again without the frequency. And okay, so again, leakage is insignificant, so you can just take it away, and you get around 2.5 picojoules, okay, per switch, I guess, okay, in this math. All right, it's very easy to calculate. Now, here's the thing, though. Although we won't be discussing it or tackling it in our class because our goal for class is really about performance in terms of throughput only and the number of cycles and understanding about trying to make processors. That's the ultimate goal. Now, over the years, we've been trying to achieve higher clock rates. However, starting from around Pentium series, actually no, Pentium 4, you'll observe that the clock rate actually saturates, right? Now, this is data, and actually, you go in the internet, determine look at the commercially available processors. We are stuck at around probably 3.6 gigahertz. Yeah, if I'm not mistaken, that's the latest. Even the commercially available processors for laptops, even desktops, we're just operating around 2.6 and so on. Okay, and then overclocking 4.0 gigahertz is already in the overclocking range. But that happened ever since around this period, around the 2000s period. Okay, on the year 2000. And the reason why is because we have this power wall. Remember, power is proportional to alpha CV squared and F. If you increase frequency even further, power increases linearly. And the problem really is that the higher the frequency, you have to submerge your processor in some liquid cooling for it to work properly. Because power dissipates heat, right? And that's the reason why you're not getting faster and faster processors. Okay. So it's making it more difficult to pack in more transistors also. Because okay, if I want to have more processing power, why don't I increase the number of transistors or the number of processing elements? Problem with that is that you're also increasing the C component, okay? Because the number of total capacitance is proportional to the number of transistors that you are using. And because of that, it's a possible improvement. Yes, not a problem, because although power is increasing due to the number of uh, transistors that you're packing in, uh, but because the only way to do it is to actually scale, make your transistors smaller. If you make your transistor lengths smaller, okay, yung mga the transistors that you have, if you make it smaller, you can pack more. Data processing units, DPU, okay, while maintaining the capacitance. Okay, the capacitance won't change. It's neutral. So that's why people are focusing more on parallelism, while scaling your transistors even lower and lower. This is why what people do, instead of actually trying to achieve higher frequency, because that's much harder to do because of the heating and all those things. What people do is, okay, why not make transistors smaller, okay, make the length smaller, and then I'll add more processing units because I mean, at the end of the day, I get more processing power, right? Or rather, I get more processing units, I get more throughput, I can process more data, and if that happens, your capacitance is not really changing much. Okay. And then you get even more benefits because for the amount of power that you're spending, you get more processing data, more parallelism or throughput. Okay. So that's the power wall scenario that we're trying to solve today. And RISC-V is trying to solve that by making better processing, by making our processors better because it can do more parallelism. Okay. Although we won't get into details with that, um, that's something that's good to know for you guys. Okay. Yeah, in summary, we need metrics that measure performances so that we can compare which processor is better, and we have performance in terms of speed, throughput, and power. Okay, what's the next slide? Yeah, so we actually have two good references. This is one good one. There's another one by Harris. It's actually uploaded in the introductory slides that we had last week. So you can look at that. That's also a good introductory. This one is a bit more, it's not an introductory book, but it's more detailed in terms of practicality. The one by Harris is more practical. So I suggest you guys read that too if you prefer to, know a bit more about this. Okay? Yep. Any questions? I think that was almost saktong 1 hour. Well, I mean, we are doing an hour and a half anyway, but I'd like to keep it within an hour only. Any questions? No questions. I will see you guys on Friday, and we will be talking about instructions, but a very, very easy version of instructions. I mean, just the basics that we need for our processors. Okay? Thank you for your time, and I will upload this on YouTube in our Microlab channel so you can check it out later. Okay, dokie? Okay, thank you, and I'll see you next week. Okay, bye. Okay, bye, bye, bye.